Have you ever stopped to wonder why that trusty mug keeps your coffee warm? Or maybe why your car's radiator needs all those, intricate fins? It really all comes down to a fundamental concept. It's quietly shaping the world around us, how heat moves. So today we're taking a deep dive into the fascinating world of steady heat conduction. Our mission, really, is to demystify how heat flows through different materials, different shapes. We want to uncover some, frankly, surprising facts about insulation and reveal the clever concepts engineers use. For designing everything from your cozy home right down to the super fast electronic devices in your pocket. We're going to show you how seemingly complex physics can actually be understood with some pretty simple analogies, giving you a shortcut to being truly well-informed about something that, well, it impacts nearly every aspect of your daily life. Okay, let's unpack this. Imagine for a moment that heat flow isn't so different from electricity. What's really powerful, and we saw this in our sources, is this concept, thermal resistance.
Yes. And what's fascinating here is that this concept draws a direct, incredibly helpful analogy to electrical circuits. Think about it. The rate of heat transfer, that's like your electric current. The temperature difference driving it, that's like voltage. And thermal resistance, well, it directly corresponds to electrical resistance. This actually means we can solve some pretty tricky heat problems without needing to dive deep into, complicated calculus.
That electrical analogy is brilliant. It really is. It makes something abstract feel so tangible. So if I'm thinking about designing, say, a new kind of insulated container, does this analogy help me quickly predict how well it will hold heat, without needing to run complex simulations first?
Oh, absolutely. It's like building a mental circuit diagram for heat flow. You can instantly see where your bottlenecks are. Is it a super insulating layer? Or maybe a weak spot where heat can leak through easily. And this applies to heat moving through simple shapes like flat walls, cylinders, spheres. And it even accounts for the heat leaving or entering their surfaces, through convection and radiation.
So it's not just about heat moving through the material itself, but also how it gets off the surface. When you say convection and radiation, are we talking about like heat moving through the air around it and also radiating out, maybe like warmth from a fire? Is that the idea?
Precisely. Yeah, convection is about heat moving with a fluid like air or water flowing past, carrying heat away. And radiation, that's pure electromagnetic waves, like how the sun warms you, right? Or how a hot stove radiates heat without even touching you. The thermal resistance concept. It neatly ties all these different ways heat moves together in one framework.
Okay, think about your house. It's a cold winter day. Heat is continuously escaping through the walls, right? It turns out that heat transfer through a typical wall, well, it can often be modeled as one-dimensional, meaning it largely moves in a straight line, more or less, from inside to outside. And what happens when things aren't changing with time? When it's steady?
Right, under what we call steady conditions, meaning the temperatures aren't fluctuating. The temperature distribution across a simple plain wall is actually linear, just a straight line drop, which is great because it allows engineers to easily calculate the heat loss. And this concept is absolutely fundamental to understanding our values for insulation. Our values at their core are simply a measure of a material's thermal resistance, how well it resists heat flow.
Okay, so a higher R value means better resistance, less heat loss.
Exactly. And to give you a real sense of this, imagine a typical wall, maybe 3 meters high, 5 meters wide, zero point 0.3 meters thick. Let's say it's made of a material with a thermal conductivity of 0.9 millOMK, which is actually quite high for a wall, by the way. If there's just a 14 degrees Celsius difference between the inside and outside surfaces, that one wall could be losing something like 630 watts of heat continuously.
630 watts, wow.
Yeah. To put that in perspective, that's like leaving a mid-sized television running 24/7, just losing that energy right through your wall. We saw an example suggesting the cost of that kind of heat loss just through house walls could be around maybe $1.44 per day.
Ouch. Okay, here's where it gets really interesting for me. Have you ever noticed how single-pane windows fog up so easily in cold weather, but double-pane windows almost never? This seemingly small change makes a huge difference, and our sources reveal exactly why.
Yes, the double pane window effect. It's a classic. If you replace a single 8 millimeter thick window glass with two thinner, say 4 millimeter glasses, and you enclose a 10 millimeter gap of stagnant air between them, it drastically reduces the heat transfer.
Just because of that air?
Precisely. Because that trapped air layer, even though air itself has a pretty low thermal conductivity, it provides significant thermal resistance. It's a great insulator when it can't move. In one example we looked at, the heat transfer rate was slashed to about 1/4 of the single pane result.
Wow, only a quarter.
Yeah, and it also had the side benefit of raising the inner surface temperature from a frosty nautical 2.2 degrees C In that example, up to a much more comfortable 14.2 degrees C, which is exactly why you don't get that annoying condensation, that fogging. It really shows the remarkable impact of strategically adding layers, especially that air gap.
That makes perfect sense for windows. But okay, what about something like, say, the walls themselves? Is it always as simple as just adding more layers? Or are there hidden complexities when heat moves from one solid thing to another solid thing?
Yeah.
I remember trying to put a new heat sink on my computer's processor once,
Yeah.
and the instructions specifically said to use this thermal paste. I honestly just thought it was to help it stick, but it sounds like there's maybe a much deeper reason now, doesn't there?
You're hitting on a really crucial point there. A subtle but important one. We've looked at heat moving through materials, right? But what happens when two different solid objects simply touch each other? You'd imagine, intuitively, if you press two incredibly smooth surfaces together, heat would just flow perfectly from one to the other. No problem.
Yeah, seems like it should.
But our sources uncovered this sort of secret culprit, something that can drastically slow things down. It's a kind of invisible barrier to heat flow, and this is what we call thermal contact resistance.
Wait, a hidden resistance? Really? Even when things look perfectly flat and flush?
Exactly. Even surfaces that appear completely smooth to the naked eye, or even to the touch. Microscopically, they're actually quite rough. Jagged peaks and valleys. So when you press them together, only the tiny peaks actually make solid contact. The valleys form these microscopic voids, these gaps. And what usually fills those gaps?
Air.
Air. Usually air. And remember how good an insulator-trapped air is from the window example? These tiny air gaps act like millions of little insulators all adding up, and that creates this thermal contact resistance. Now, this resistance can be really crucial, particularly if you're dealing with good heat conductors like metals. For poor conductors, like insulation materials themselves, it might be negligible, you barely notice it. But for metals trying to transfer heat efficiently, it can be a big deal.
So that thermal paste on the computer chip.
That's exactly it. That thermal paste isn't just glue. It's a thermally conductive material, usually a liquid or paste, like silicon oil-based stuff.
Yeah.
It flows into those microscopic gaps, pushes out the air, and provides a much better path for the heat to flow across the interface. You can also minimize it by using better conducting gases in the gap, like helium or hydrogen, if possible. Or even by inserting very thin, soft metallic foils like tin, silver, copper that deform and fill the gaps. Just to give you some context, the thermal resistance of just one interface could actually be equivalent to the resistance of, say, 2.23 centimeters of solid copper.
Wow. That's a significant chunk of copy just to match the resistance of a seemingly perfect contact.
It really is. It highlights why it's so important in things like electronics cooling.
Okay, this next one. It feels a bit like a brain teaser. Most of us, myself included, intuitively believe that adding more insulation always reduces heat transfer. It's like putting on another sweater, right? More layers, warmer you stay. Simple. But what if I told you that for pipes, or maybe spherical containers, adding insulation can sometimes increase heat transfer? Wait, hold on. So you're telling me that adding insulation, which we always think of as keeping things warm, could actually make a pipe lose heat faster? That sounds completely backwards. Can you give us like a really concrete, everyday example where someone might accidentally make this mistake?
Exactly. It feels totally wrong at first, doesn't it? It's a real paradox. And it leads us to this fascinating concept called the critical radius of insulation. Here's the thinking behind it. Adding insulation, yes, it definitely increases the material's conduction resistance. That's the sweater part, blocking heat flow through the material itself. But simultaneously, it increases the outer surface area of the insulation.
Okay. Bigger surface on the outside.
Right. And a bigger surface area means more area for heat to escape into the surrounding air or environment via convection. So increasing the outer surface area can actually decrease the convection resistance at the surface. Heat has an easier time leaving from that larger area, so you have these two effects working against each other. Adding insulation increases conduction resistance, good for stopping heat, but decreases convection resistance, bad for stopping heat.
Okay, so which one wins?
It depends. If the outer radius of the insulation you've added is below a certain specific value, this critical radius, which, by the way, is calculated as K divided by H. K is the insulation's thermal conductivity. H is the convection heat transfer coefficient from the surface. Then adding more insulation, making the radius bigger but still below critical, can actually increase the total heat transfer. Because in that range, the benefit of the increased surface area for convection outweighs the benefit of the added insulation thickness.
That's truly counterintuitive. My mind is slightly blown.
It is. It catches everyone out the first time they hear it. Now, the good news, perhaps, is that for most common insulating materials and typical natural convection situations, this critical radius is usually very small. often around 1 centimeter, maybe even less. So for most practical things like hot water pipes or steam pipes in buildings or industry, they're usually much larger than this critical radius to begin with, which means adding more insulation to them does generally reduce heat loss, as you'd expect.
Okay, phew. So my intuition isn't totally broken for normal types.
Not usually, no. But there are specific cases. Think about very thin electrical wires. The thin plastic insulation coating on them might actually have a radius that falls below the critical radius of the conditions.
Right.
So, ironically, if you made that plastic insulation just a little bit thicker up to the critical radius, it might actually help cool the wire more effectively by increasing heat loss to the air.
Wow. Okay, so insulation isn't always about keeping heat in. Sometimes it helps get it out.
In certain specific scenarios, yes. It's all about balancing conduction resistance through the material and convection resistance from the surface.
Right. So we've been focusing quite a bit on keeping heat in or maybe accidentally letting it out faster. But what if your goal is the opposite? What if you want to get rid of heat? Think about your computer processor running hot, or maybe a car engine after a long drive. Engineers need clever ways to shed heat quickly and efficiently. And it turns out the solution might even have a prehistoric origin, which is kind of fun. So if we want to get rid of heat, enhance heat transfer, what do engineers do? The answer we found lies in finned surfaces, fins. And here's that surprising historical tidbit. Some paleontologists speculate that even dinosaurs, like the Stegosaurus, might have used those large bony plates on their backs, partly as cooling fins, though that's still debated, of course.
That's right. Whether Stegosaurus did or not, the principle is sound. Fins work by dramatically increasing the total surface area that's exposed to the surrounding fluid for convection and also for radiation. More surface area means heat can escape much more quickly. This principle is absolutely vital in devices like car radiators. You see all those thin metal sheets packed together. Those are fins. And electronic heat sinks those metal blocks with spikes or plates on top of computer chips. Fins again. They keep your computer from melting down.
So it's all about maximizing that surface area.
Primarily, yes. And the effectiveness of a fin also depends heavily on the thermal conductivity of the fin material itself. You want the heat to travel easily from the base of the fin out to the tip, right? Which is why fins are typically made of highly conductive metals like aluminum or copper. The fin's length and shape also play a big role, of course. Engineers use concepts like fin efficiency. That's a measure of how well a real fin transfers heat compared to an ideal, perfectly conductive fin of the same size. And also fin effectiveness. That's the ratio of heat transfer you get with the fin compared to what you get from the same base area without the fin. It tells you how much improvement you got. Yeah. We saw one example where using a specific design, parabolic pin fins, achieved something like a 10-fold increase in heat transfer compared to the base surface alone.
A 10-fold increase, that's huge.
It is. And that kind of improvement is critical for cooling modern electronic components. You have to manage the thermal resistance of the entire cooling path, including the heatsink, very carefully to keep those devices operating safely.
Okay, so we've covered simple shapes like walls and cylinders, we've looked at interfaces, the weirdness of critical radius, and boosting heat transfer with fins. But how do we pull all this together for more intricate real-world situations? Like, say, heat flowing through complex building walls with studs and insulation side by side, or figuring out heat loss from pipes buried underground. We're not always dealing with flat, perfectly uniform insulated boxes, are we?
No, definitely not. The real world is usually messier. This is where engineers really lean on those thermal resistance network concepts we talked about earlier. For systems with multiple layers or different materials next to each other, you build up a network of resistances. Think of it this way. Resistances can be combined in series if the heat has to flow sequentially through each layer. Like through plaster, then insulation, then brick and a wall. You just add the resistances up.
Okay, like resistors in series in electronics.
Exactly the same idea. Or resistances can be combined in parallel. This happens when heat has simultaneous alternative paths you can take. The classic example is a building wall with insulation between wooden studs. Heat can flow through the highly insulating paths, the insulation itself, or it can flow through the less insulating path, the wood studs. Those are parallel paths.
Ah, so the studs act like thermal bridges, letting more heat through.
Precisely. They short-circuit the insulation to some extent. You have to account for both paths in parallel to get the total heat loss right. And for more complex 2- or 3-dimensional geometries like corners, edges, or buried objects, where the heat flow isn't just straight, that's where engineers use something called conduction shape factors.
Shape factors, okay. So these are like pre-made blueprints or formulas for engineers. They don't have to redo incredibly complex math every single time they encounter a common setup, like a pipe buried in the ground or a specific corner of a building.
Exactly. You've got it. Think of them as a massive library of solutions, a huge shortcut. Researchers and engineers have already done the super complicated calculus or simulations for countless common shapes and configurations, like spheres buried in the ground, pipes parallel to surfaces, corners where walls meet, etc. And they've boiled down the result into a relatively simple geometric factor, the shape factor, often denoted by S. You look up the shape factor for your specific geometry, multiply it by the material's thermal conductivity, K, and the overall temperature difference, and bam, you get the total heat transfer rate, Q, same damn mirror. It saves an immense amount of time and effort in design and analysis.
That sounds incredibly useful.
Oh, it is. For instance, we looked at an example, a 30-meter long, 10-centimeter diameter hot water pipe buried 50 centimeters below ground. In soil with a typical thermal conductivity, say kk 0.9 Willer/MK. Using the appropriate shape factor for that geometry, you could calculate that the pipe would still lose approximately 1,100 watts of heat.
1,100 watts,
Yep.
just buried underground. Wow.
Yeah, the heat loss from buried utilities can be significant. And similarly for building walls, really understanding the overall effective R value involves accounting for all the layers in series, but also those parallel paths, those thermal bridges like studs or metal fasteners, using these resistance network ideas.
We've really journeyed quite far, haven't we? From the foundational concepts of heat flow, using that brilliant analogy of electrical circuits, all the way to real-world applications in our homes. That surprising paradox of critical insulation, and the clever designs of fins and these complex structures using resistance networks and shape factors. It's incredible, isn't it, how these seemingly simple principles of heat conduction underpin so much of our daily lives, often unseen. I mean, I'm still blown away by that critical radius idea. Who knew adding insulation could actually increase heat loss sometimes?
It really makes you appreciate the nuances, doesn't it? It's not always straightforward.
Absolutely. So, for everyone listening, you now have a much better handle on the power of the thermal resistance concept. You understand that counterintuitive behavior of the critical radius, and you see how engineers optimize heat transfer, both reducing it and enhancing it for everything from keeping you comfortable to ensuring your electronic devices perform at their peak. So, here's a thought to leave you with. Now that you've seen how a seemingly simple concept like steady heat conduction can reveal so much about the world around us, what other everyday phenomena, things you see or interact with all the time, might be hiding equally elegant underlying principles just waiting to be unpacked? What are you curious to deep dive into next?